What's going on, guys? So we're going to be going over some more quantum mechanics review before we dive into quantum field theory. What I want to do here is we want to talk about some more properties of matrices, right? So in the last video, we talked about matrices as being these things that you can exponentiate to get more global transformations. In this video, we want to talk about their non-commutation relationships and how that's going to be relevant to quantum mechanics as well. Again, if you like this kind of content, you can go onto my Patreon page and contribute there, or you can really just hit that subscribe button, and that's awesome as well. So let's get right into this. If we want to take, for example, this matrix where we have just an identity matrix, and we can multiply it with, say, a matrix that looks like this. And then we take the difference between the ordering. So we just reverse the order of these two matrices. What we'll get is that this, if you remember anything, if you remember anything about matrix multiplication in linear algebra, this isn't going to be a review of linear algebra, but if you remember that what you'll get here is I 0, 0 minus I and minus negative I 0 I. These two matrices are not the same, right? In fact, these two matrices will give us, and because one's the negative of the other, and since we're subtracting it, we're getting 2 times the other. So this is not 0, right? In other words, matrices are not like numbers, right? You can have a number, say 5 times 8 minus, if we did 8 times 5, that's that's 40 minus 40, right? So that's going to be 0. Matrices, it's not that way. We're seeing right now that in the case of matrices, the difference between the ordering of the two is not 0. And this is what we mean by non-commutation, a non-commutation relationship, right? They don't commute, right? And there's another way of writing this. You can write, say, we have matrix I, which is this one right here, and matrix sigma, which is this one right here. If we do I comma sigma, that does not equal 0. This is a non-commutation relationship, okay? Again, this is a lot of review, but if you don't know, this notation really means I times sigma minus sigma times I, right? So just to be a little bit more clear, this is the same thing as I times sigma minus sigma times I. And so maybe I'll do so this point right here, that the fact that this doesn't equal 0 means that these two things don't commute. The punchline here is that numbers commute. The punchline so far is that numbers commute, right? So name any particular number of interest, right? So 4 times 6, that's the same thing as 6 times 4. However, matrix 1 times matrix 2 is not the same thing as matrix 2 times matrix 1. So that's just a little bit this is a little bit of a foundation on group theory too, but we won't go into that quite yet. Right, so I'm going to erase all of this now. We're going to get into some more interesting stuff here. Again, this is a review on quantum mechanics, not a full-on course. So I'm just going to go through some of the important points that are going to be brought up in this book again. Again, you're interested in following along. This is the book, No Nonsense Quantum Field Theory by Jacob Schwittenberg up here. And we are on chapter 7, I believe. We're getting far into this chapter. Let's take a look now at this object right here. So we're doing a commutation relationship between something that we're calling pi and something that we're calling xi. Right, so the p is the momentum of some system, right? And the I refers to some part in that system. So you can imagine you have a ton of small objects and they're all moving in, say, some one direction. I, so P1, for example, P1 refers to the momentum of one of the objects, P2, momentum of one of the other objects within this overall system, right? So we're looking at a system of particles that all have their own momenta and they all have their own position. And we want to take a look at we want to see what we know in quantum mechanics is that these two things don't commute as operators, right? Matrices operate on vectors. Momentum and position act on eigenstates, or not they act on states of a system. The system, a quantum system, is described by a state, right? The state lives in a Hilbert space. If you don't know what that means, it basically means that it's a vector in a multi-dimensional space where each dimension represents a possible outcome of your system, right? Or a possible state that your system is in. And the idea here behind quantum mechanics is that the vector, the weight on each dimension that constructs the vector, is a likelihood, perhaps, of what the system is likely to be in, what state the system is likely to be in. We can think of this as, if we're just thinking in 3 dimensions, and this is our state vector, right? Each dimension, so like say this dimension right here, x, I don't want to use x, and I don't want to get too much into this. Here's our vector. It has this much on this axis, right? There's a weight on this axis, and there's a weight on this axis as well. These weights, again, are, if this is, or if the red one is given by some state, phi, then the blue one here, for example, the blue weight on this dimension can be a particular state that this is in. Not a particular state that it's in, but a possible outcome of the state. And then perhaps there's another possible outcome that the state could be in. And I will actually do this as yellow, right? Because one other state, again, is lying on that x-axis there, right? So the state, again, is a superposition of multiple states that our system can be in. That's all I'll say on that, because, again, this is not a full-on course on quantum mechanics. And, okay, now I want to get back to this color here. The idea here is that pi xi minus xi pi acting on the state. What we are told in quantum mechanics, not what we're told, but what we learn in quantum mechanics, is that these states, they correspond to some operator the momentum operator corresponds to a derivative times xij. These need to be j's because we're looking at different momentum in one state acting on the position of a different state. And I and j can be of a different particle or a different independent variable within your system. I and j can be different. They can also be the same. This is going to be plus xj minus h di. So if you don't know, again, this here is right, that's our pi, and then our x is simply multiplying our state by some position x, right? So the momentum, it corresponds to taking a derivative of your state, spatial derivative of your state. The position that your state is in, it corresponds to multiplying your position by some position value, just x, right? And actually, I want to get rid of these hats because they're no longer operators in this case, right? So we're going from here, operators, with these hats, operator notation, if you will, to actually seeing what these operators are, okay? And then, well, this is going to be equal to IH bar DI XJ. We are really just adding things up here. Okay, and then what we get next is IH bar DI XJ, and then minus, because the idea here is we're taking the derivative of, here, I'll write this out first. I can't speak and write at the same time. IH bar DI, oops. Like that. And then plus xj minus IH bar DI, like so. So how did I do this? I went from saying that this is the thing I expanded, not this, right? So this right here is this right here. This guy right here is right here, we're seeing it right here, but what's this? Well, this is the derivative acting on this one, on the state, right? On the state right here. This here is a derivative acting on this, right? So this is really just a product rule, right? This is just product rule. Well, what we're seeing now is that this and this are the same, but we have a minus sign right here, so they cancel, okay? What we get is the following: minus I H bar IJ right, and this is not equal to 0, right? What's this thing right here? This is Kronecker delta, right? So Kronecker delta is that this is going to be 0 when I and j are the same, but when they're not the same, then we don't get 0. And this shows, what does this show? This shows that the commutation relationship between momentum and position is not equal to 0, okay? Just like we've seen with those matrices, these two operating matrices, or the two operating matrices that we took as an example, they did not commute, right? This is all to say that you cannot, this is the mantra in quantum mechanics here, is that you cannot know the position and the momentum of a system to arbitrary precision at the same time. This is what gives rise to quantum fuzziness, right? And this is what's going to give rise also to very important relationships, and it's going to help us understand annihilation creation operators in the context of Klein-Gordon and Dirac Lagrangians. Also, this is going to be, and those things are sort of going to be the defining features of quantum fields. Okay, so this hydrogen, or this is also not hydrogen. This is also somewhat understood as the Heisenberg uncertainty principle, where you can't know position and momentum at the same time. And this really all comes again from the proposition that they can be described as operators acting on some states, and the states being these things that describe probabilities that your states are in. Okay. So what we want to do now is we want to consider, we're thinking in our mind now that these states, they can evolve in time, right? So these states, they're functions of position and time, right? But we can rewrite them in time as being these things that don't rely on time, but are operated on by some time evolution operator. That's what we're calling this right here, this U. Okay, this is a time evolution operator. Okay, and what this time evolution operator does, what we can consider, again, the time evolution operator takes your vector, and it just moves it in time, right? Okay, and it's operating on our state. We can apply the Schrodinger equation to this time evolution operator. Right, we're really just applying, this is our Schrodinger equation. So I'm rewriting Schrodinger equation. If you don't know what the Schrodinger equation is, again, that's something that's covered in standard quantum mechanics. I will make a standard quantum mechanics playlist, but not here, right? We're talking about quantum field theory. Again, this is just review. Well, this is the Schrodinger equation. This is the Schrodinger equation, and if we take now the time evolution operator and we put this in replace of our Schrodinger equation, in replace of our states, this is what we get. Right? So we're really just putting this guy in replace for these guys right here, right? So we get this, and then what we can do is we have this is actually should be a 0, x 0. We can divide both sides by our state. Okay, and what we get is that the time evolution operator must obey this equation. Okay, and this is a differential equation. Right, this differential equation can be written like this. where we have our u of t, time derivative of u of t divided by u of t equals h. If you recognize this as a differential equation, what you'll find out is that the solution to this, if you kind of need to have taken differential equations a little bit, but the solution to this equation is that u of t has a particular form in this case, and that u of t, so therefore u of t has this form to it. And this is extremely, extremely important. The reason this is extremely important is that we won't check it, but you can plug this in to this, right? Plug this in to this and find out that what you'll get when you plug it in is that h equals h. And that's that means the thing we proposed to be a solution to this actually worked. Right? This is important. This is a time evolution operator, and this is extremely, extremely important, and what's going to be later to come. So this means that the time evolution operator looks like this, and so if we plug this back in to our state, this is equal to e to the minus I h bar from 0 to t dt h of t prime. We need a prime up here also, because that dt prime is the integration, the variable of integration, times x, right, where this here is u of t, right? So this is how our states evolve. And this is important. These two equations are important. So considering that the Schrodinger equation is true, we therefore are forced to understand that the time evolution operator must obey the Schrodinger equation, and sort of by fiat, therefore, we have the time evolution operators being some exponential of some integral, okay? So the operators that we have look like this now. We have our PI operator, or momentum operator. We have our position operator, and we have our time evolution operator. Okay, these are, I want to circle these because these are the big operators here that are going to be dealt with in quantum mechanics for the most part, right? There's other types of operators that you're going to want to be interested in because they all have interesting properties to them. But the three big daddies here, or the three big players here, are going to be these three, right? The momentum operator, the position operator, and the time evolution operator. Okay. So I'm coming up on 30 minutes again. If this is the kind of content you like, please hit that subscribe button. If you want to donate to this channel, you can go to my Patreon page. And yeah, so the next video, I think we might be going over a little bit more quantum before we get into quantum field theory. So what we want to do next is go over a projection operator, right? So we're going to go over a projection operator, which is also going to be really important in quantum mechanics. Then we're going to want to do a brief review on harmonic oscillators, because again, those are very important in understanding quantum mechanics and quantum field theory. And then we're going to get into quantum fields. And that's the next big chapter in this book. So we're still in the quantum mechanics review, but we really only have 2 videos left before we get into quantum field theory, which is going to be really fun. We're going to go deep into it, and yeah, I have some good prospects for this. I'm also realizing I'm coming up on video 30 of this playlist, which I think is a pretty neat accomplishment. But yeah, so I'll see you guys on the next one. I won't repeat myself, but have a good rest of your day, and I'll see you guys in the next one.